Hey, good morning, Elch2. Hope you guys had a good week so far this week. We're going to finish up the week here on Thursday with lesson 8.5, day 1. We'll do day 2 next week. And I guess I should say it's talking about infinite geometric series, and it's actually finding the sum of an infinite geometric series, okay? So to do after our lesson today, we're going to ask you to go complete your 8.5 day 1 try on your own, and also please make sure you submit your homework by Monday night for this week, which should be, what is it, 8.3, 4, and 5, day 1, I think. Just make sure you double check that. Also check It's Learning. There could very well be a formative assessment housed in It's Learning covering 8.1 to 8.3, all right? And after that, what we're going to do here is we're going to start with a warm-up. I'm going to hit pause. I'm going to do these. You learned how to find these sums of arithmetic sequences last week, and you found how to find a finite sum of a geometric series on Monday and Tuesday in 8.3. So I'm going to hit pause. Once you come back, do these 4 quick, and I'll have the answers for you. Okay, here, so for number 1, first thing you got to do is you got to identify that as an arithmetic sequence. And what you do, remember, arithmetic sequence, it is your first term plus your last term times the number of terms divided by 2. That's how we find an arithmetic. And my geometric sequence over here, my sum is actually going to equal, what is it? It's my first term times, I got to get a little bit more room here. So what I'm going to say is this one's a geo, and I need a little bit more. My sum of my n terms is going to equal, what is that? What is that little bugger equal? It's my first term times my common ratio raised to the number of terms being summed minus 1, and that whole thing gets divided by my common ratio minus 1 is typically the formula we will always use when we are in summation notation. So the first one, we're cruising along here, is the first term is 32, the last term is 64. Remember, the first term is simply found by putting that lower limit in here and finding that's 32, and the last term, 64, is gotten by taking the upper limit and plugging that in there. And then also remember the number of terms, 9 right here, that's not necessarily that 9 on top. It's the upper minus the lower plus 1 to see there's 9 in this case, which gives me 96 times 9 over 2, which is 4.5 for the decimal freaks. You multiply those two. The sum of those terms is 432. Number 2 is geometric. And because it's 5, I actually want 5 of those sums. Now notice it's the sum of 4 terms because I'm starting at 3, going to 0, adding my initial term. That gives me 4 terms I'm summing. So that's one of the another time where you can't just assume the top of that thing, the top of your summation is n, the number of terms being summed, because it's not. So what we do is we're taking 5 times this sum, which is my first term. 4 to the power of 0 is 1. My common ratio is 4 because that's what's getting raised to the exponent to the number of terms is 4 minus 1 as always divided by number my common ratio, 4 minus 1. Well, that gives me 5 times the quantity there of, you simplify that top, well, 4 to the 4th power is 256, and if I subtract 1, I get 255 times 1 is 255. If I divide that by 3, I get 85, and I really wanted, in this case, I wanted 5 of those sums, so it's 425. Okay, my last 2 down here, number 3 is also geometric, and this is the sum of 4 terms because my upper minus my lower plus my initial term gives me 4 terms in this case. Well, when I plug my lower limit in there, I get 1/2 to the power of 0. Anything to the power of 0 is 1 times 12. So my first term is 12 times my common ratio is 1/2, which is 0.5 for the decimal freaks, raised to the number of terms we have, minus 1 all over my common ratio minus 1. Well, if I type that top in there, a half to the fourth power minus 1 times 12, that's negative 11.25 divided by 0.5, that gives me 22.5. And the very last one there, hey, we got another arithmetic sequence. This one's actually subtracting away. So my first term, how many are there? Top minus bottom plus 1. So that's actually going to give me 8 terms. Notice that's why I'm taking the sum of 8 terms over here. My first term is plugging a 0 in there to get 55. My last term is plugging a 7 in there to say 55 minus 70 is negative 55 times 8 over 2. So I really get 40 times 4, which is 160. Okay? So we're cruising along here. And so far, we've explored finite series for both arithmetic and geometric. Now we're going to start thinking about the question, can we find the sum of an infinite arithmetic sequence? Now, what we're first going to do is we're going to write out a few terms and explain why not. What do you mean first term? Well, remember, this is going to equal A1 plus A2 plus A3 plus ... plus all the way down to my last term. So let's write a few of these out and see what we're gonna, what type of sum we would get if we're summing from the first one to infinity, meaning I'm never stopping adding together. This is kind of a weird concept, but my first term, if I plug 1 in there, I get 16 plus, now I plug a 2 in there and I get 20 plus 3 is what, 24 plus 28 plus ... and I'm going to continue adding all these together. Well, what happens if I continually add all those numbers of this particular sequence, which is arithmetic, by the way, because it's a linear function or a linear sequence? What happens? Write out the few terms. Can we find the sum of an infinite arithmetic sequence? Yes or no? Well, what is this going to add? If I continue to find the terms, what is that going to add to? Well, no, there's not going to be a sum. And the reason there's not going to be a sum is, check this out, my terms keep getting bigger and bigger and bigger and bigger and bigger. And if I keep adding them all up, what are they going to sum up to? They're going to sum up to infinity. And please understand, infinity, that is not a number. Infinity is a concept. So how big is it? We don't know because it keeps getting bigger. So there would be no sum for any arithmetic sequence. Nope, we cannot. And the reason is what if you say, well, what if my numbers are getting more negative? Well, they're getting more negative. They're going to sum towards negative infinity. They are not going to, quote unquote, converge to a particular number. Infinity is not a number, it is a concept. Well, let's keep rolling the dice here. Well, let's explore a couple infinite geometric series here. And just to throw this together, we'll have a couple visual samples. Well, if this is my sequence that I got here, okay, and I want to add those together, what am I doing? Well, the first one is I'm taking a third of a pi, and then the next one is I'm going to take a third of that third, which is a ninth, plus, then I'm going to take a third of that last third I got, okay, which is a 27th, and if I sum all these numbers together, okay, what's going to happen? Well, what do we notice? Each piece that was added to the piece, is it becoming bigger or smaller? Well, it's getting smaller, right? Because we can see it's getting smaller. So if we imagine if this whole thing was a pi, okay, and you got the 20th term in this pi, is it going to be a really, really big piece of pie, or is it going to be a really, really small piece of pie? It's going to be small, isn't it? And you're not going to be happy because who doesn't like pie, right? We like pie. So let's check this one out. Well, a new sequence, right? And as I'm finding my terms in this sequence, the first term's 1, second term's 3, next term's 9, next one's 27. Each time a piece is getting added, well, did that piece get bigger or smaller? Well, this time it's getting bigger, right? So, as my pieces are getting bigger, if we're picturing the 100th term, is that going to be a really big number, or is that going to be a really small number? That is going to be big. That's why I'm going capital. It's going to be bigger, bigger, bigger. My terms are getting bigger, bigger, bigger. Well, how about here? How about on my ruler? Here's my sequence I got going on, and I can see there's the first measurement I add, then there's the next measurement I add, there's the next measurement, and the next one. So there's 1, there's 3/4. So these are my terms. Okay, my first term, 1. My second term, 3/4. The next term is 9/16. Well, what's going on? Was the added piece bigger or smaller than the previous piece? And smaller, right? I can see that. I can see it up here as I'm adding further down the line. Excuse me. Those pieces are getting smaller. Well, here's the last one. Here's my sequence I'm looking at. Hopefully you're focusing on the sequence. It's pretty much a big deal. That's why I keep circling the sequence, because it's the sequence that I'm looking at that's telling me, is my piece getting bigger or smaller? And on this one, I can see my first piece of the pie, well, it's a 4th. The second piece of my pie is a 16th, so there's a second little piece. And if you're third in line in this sequence, well, heck, you're getting a piece of pie that's a 64th. Well, do you want to be the first person or the third person, or do you want to be the 10th person down the road getting your piece of pie? Well, I want to be right here, because as these pieces are cut, they're getting smaller and smaller and smaller, right? So the added piece is getting smaller, which is kind of odd, you know. It's thinking, you can get down there, you got to have a good pie cutter for that. So this is going to make us talk about a convergent series and a divergent series. And what a convergent series is when our pieces are getting smaller. Okay, so the term number we're adding down the road, like the piece of the pie, the further down the further down in line you are, the smaller piece of pie you get. That is called a convergent series. And in a convergent series, the sum exists. And it's because it converges to a particular number. Okay? If my pieces of pie or my pieces of things that I'm getting, my terms, if my terms are getting bigger and bigger, well, my sum doesn't exist because it diverges. Okay, divergent means I am approaching a positive or negative infinity. Okay, so the next question we have in line here is, why does the sum exist in a convergent series and not a divergent series? Well, did you look? Did you pay attention to all of these guys? Hey, my pieces are getting smaller. This is a convergent series. Here my pieces are getting smaller. Are you connecting the dots between your functions? It's a convergent sequence. This one, ooh, my pieces are getting bigger. This is a divergent one. This one, my pieces are getting smaller. It's convergent. Did you pay attention to those as we went along? Well, here it is. Why does it? Well, the pieces get smaller and smaller each time, which means the size of each piece begins to approach infinity. Not right away, but the further down the road you get, how much you're actually adding to that sum is a sliver of what you had before. So eventually, what really happens is what I'm adding to it is really nothing, okay? And I stop getting a sum because the piece I'm adding is so small. That's why you want to get the piece of pie first in a convergent sequence. Well, what value determines whether a geometric series is divergent or convergent? Did you put that together? Did you put together what it is? It is the ratio, okay? That's what it is. It's our little r we're talking about in our series. So, when dealing with infinite geometric series, you must first decide if the series is convergent or divergent, okay? Well, this is really a pretty big deal, especially if I'm trying to find a sum, because if it's convergent, I know it's convergent because my absolute value of r is going to be less, not than that. It's going to be less than, what's it going to be less than? It's going to be less than 1. That means the absolute value of your common ratio is going to be a fraction, and it's bigger than 0, but it's going to be less than 1. It's going to be sandwiched somewhere between 0 and 1, okay? And that's how we're going to put it. Well, knowing that it's convergent, if you have a ratio that's between 0 and 1, Okay, well, we have now a special formula that we will be allowed to find the infinite series, which is the sum, okay? It's the sum of the infinite number of terms down there, and all I need is my first term, and I divide it by 1 minus my common ratio, and I got it, okay? Now, if my function is divergent, okay? If it's divergent, convergent, when r is between 0 and 1, absolute value of r, it's divergent when? Well, when do you think it's divergent? Well, that's when r is bigger than, I did it again, not 0. It's when r is actually bigger than 1, okay? In knowing that a series is divergent, the sum is either infinity or negative infinity, which means it does not exist, okay? Well, I'm ready to try a couple. I don't know, how about you? Well, is this series going to be convergent or is this going to be divergent? Well, that depends. There's my common ratio. How do I know that's my common ratio? Because that's what the power is getting raised to. Okay, my exponent is always on my common ratio. 1/3, absolute value 1/3, that's between 0 and 1. This must be a convergent series. And if it is, they want us to find the sum. Why is it? Well, that's because r is a third. Okay, r is a third, and if it's a third, and what's a third? A third, or it's 0.3 repeating for the decimal freaks, but it's really hard to subtract 0.3 repeating. I'm telling you what, it really doesn't work. So we really kind of need to think of our common ratio as a fraction. So the sum of my infinite terms is going to be my first term. Well, what do I get when I plug 1 in there? What's 1/3 to the 1 power? That's 1/3, and that is going to be divided by, what's that going to be divided by? 1 minus my common ratio of a third. Notice, for your finite geometric sequences, it was your common ratio minus 1. Now that denominator switches. It's 1 minus the common ratio, and then as I slice this, I get a third divided by, well, 1 minus a third, well, that's 2/3. Oh my God, I'm dividing fractions. No, I'm not. I'm taking the top one times the reciprocal of the bottom one. Whoa, whoa, whoa. Come on, Kruger. Get this written right now. Yeah. I got to take the top one. What the heck was the top one? A third times the reciprocal of the bottom one. And the beautiful thing is bam, bam. Ooh, it's a half. So the sum is going to equal 1/2. My infinite sum. If I take a piece of pie, okay, and I keep cutting each piece 1/3 the size of the piece before, okay, I'm only going to cut half the pie. That's what this is telling us. It's kind of weird to think about that, but it's going to get so thin that you're going to be taking 1/3 of a crumb. Wow. How about this second one? Well, is this one going to be convergent or divergent? Well, I don't know. That all depends on r. What's r? Remember, r is what the exponent is on, so r is 3. Convergent or divergent? Well, I think I remember we said if the absolute value of r is greater than 1, it's divergent, okay? So this one's divergent. Why is this divergent? It's divergent because basically the absolute value of r, it's greater than 1, and r equals 3. Or we're thinking the absolute value of 3, yeah, that's bigger than 1, and this means divergent. So what's the sum? Well, here's your favorite part. I don't care. I know my sum is going to be infinity. I can see my sum is going to be positive infinity, which means there is no sum because it's going to get bigger and bigger and bigger. Okay? Now there's try number 3 and 4 on your own here quick. I'm going to hit pause and I'll be back. You try these next two, see if you get them right. Okay, and we're back here. What'd you come up with, number 3? See, I didn't circle mine. R equals 3/2. If r is 3/2, is my series convergent or divergent? I hope you didn't fall into the trap that, oh, it's a fraction, it's convergent. Because this is divergent, because this actually equals 1.5, which is greater than 1. Therefore, it's divergent, which means what? Yep, there's no sum. And it's infinity, it's positive infinity, because I can see all these numbers are positive, okay? And my last one, well, there's r, 1/4. Is this convergent or divergent? This one must converge. Why? Basically, my absolute value of 4 is less than 1, but I don't even need to say greater than 0 because it's less than 1. Doesn't matter. If I didn't use the absolute value, it would matter. But so it's divergent, which means I'm taking my first term of 1/4 and I'm dividing it by 1 minus my common ratio, which is going to take me to 1/4 divided by 1 minus 1/4, which is 1/4 over 3/4, which is actually the top multiplied by the reciprocal of the bottom. My 4's cancel out beautifully. My sum, it's a turd. Isn't that nice? It's a dirty, rotten turd. So the last page we got going on here. Write the infinite series in summation notation. Okay? So first and foremost, I'm going to hit pause. I'm going to do the first one. I'm going to do the first two with you. Okay? And then I'm going to pause it, and you're going to do the rest of them. And I'm going to come back with the answers. So, and then we're going to identify if the sum exists. So first and foremost, I need to identify what kind of sequence of series this is. Hey, this is an arithmetic, so I know a sub n is going to be my first term plus my common difference of 4 times n minus 1. Now, just because this is an arithmetic sequence, so is my sum going to exist, yes or no? Hopefully you're going to answer that no, because the only infinite sum that exists, it has to be a geometric, but that doesn't mean I can't write this sum as an infinite summation. I can say my sum is going to start at n equals 1, and it's going to go on forever of my 8 plus 4 times n minus 1. Okay, remember, I have to be in variable harmony here. These guys got to match. Whatever my index is, my variable and my function has to be there. So that's my sequence written in summation notation. It's just no sum. Okay, it has no sum. Why? Because it's an arithmetic sequence. That's all I need to know about it. Now over here, what do I see? 9 to 3 to 1 to a third. Ooh, looks like I'm multiplying by a third. Everybody's going to tell me I'm dividing, but this is g sub n is my first term times 1/3 raised to the n minus 1, isn't it? Well, I can write that in summation notation. My index is going to start at 1, and it's going to go to infinity, or my first term times 1/3 raised to the n minus 1. Now, what is r? R is a third. What does that mean? That means this sum exists because r is less than, or the absolute value of r is less than 1. So my first term, be careful, what's my first term? When I plug a 1 in here, what's 1/3 to the power of 0? It's 1 times 9. So I get 9 is my first term, divided by 1 minus r, which is a third. Well, that's going to give me, what's that going to give me? 9 over 2/3, which is 9 over 1 times 3 over 2, which is 27 halves, which is what? Oh, for the decimal freaks, or I can call it 13.5. So, does the sum exist? Yeah, what is it? Right there, just found it. So why don't you guys do the next 4, and I'm going to come back and I'm going to have the answers for you. All right, well, I can see here I got an infinite error, or no, where am I? Am I on the right one or am I on the wrong one? I'm on 3. So I do, okay, so here it is. I got a geometric sequence. I wrote those. Okay, so you had to write it in summation notation. If you didn't, you got it wrong. Okay, the question isn't just if it does find the sum. So here I can see my r. Here I can see my r. Do those two have a sum? Absolutely not. Why? Because the absolute value of my r is greater than 1. Therefore, there is no sum because the terms are going to be getting bigger or bigger negatively, meaning approaching positive or negative infinity. When I'm looking at number 5, that's an arithmetic sequence. There ain't no way that's going to have a sum because my numbers are going to get more and more negative. Check it out. They're getting bigger negatively. What do you notice about these guys? They're getting smaller and smaller. This little devil, check it out, there's r. R is great. The absolute value of it is less than 1. Therefore, it's going to have a sum. The other one did not because it's arithmetic, but I take my first term 20 and I divide it by 1 minus the common ratio. Minus a negative is a positive. That's why I got a 3/2 on the bottom, which is the top, 20 over 1 times the reciprocal of the bottom, which gives me 40/3 or 13 1/3 for the other ones. If you write down 13.3, it's wrong. 13.33, it's wrong, okay? The sum is right there. It's what it is. No decimals allowed there. Last one. Am I going the wrong way here? So now we have two problems. We have friction and air resistance cause a swing. Okay, so our swing, bottom line, read it. Pendulum bob to be 9.9 times as long. So we're sitting here on a swing. Ooh, it's going this way. And the first one is it goes 16. Then it's going to come back 90% of that. Then it's going to come back 90% of that. Then it's going to come back 90% of that. Look at that. Each swing is getting smaller, so I should be able to calculate the total distance of my pendulum by the time it ended. This is, do you know how many times it swung before? I certainly don't, so I'm going to identify it as n equals 1 to infinity. And what would it be? Well, remember, your G sub n is your first term, 16 times your common ratio to the n minus 1. So if I'm finding this sum, I plug my 1 in here, okay? 0.9 to the power of 0 is 1 times 16 gives me 16 divided by 1 minus my common ratio. Well, that gives me 16 over 0.1, which equals the old decimal shift, 160 over 1, or 160 centimeters, okay? I would really appreciate if you tried the next one on your own first. I'm going to go through it right away so I can shut this video down. But a ball is dropped from a height of 30 feet. Each time it drops, it rebounds 75% of the height from which it's falling. Find the total distance traveled. Find the total distance traveled until it stops. Well, what does that mean? Well, I got my ball right here. I drop it, and it goes down 30 feet. And then right there, if that's the ground, it goes whoop, and it comes back up. I went too far. It comes back up 75% of it. Okay, so we'll say that's about 75%. And then it's kind of suspended, then it goes point down, and it comes back up 75%, and it goes down, and then it bounces, it comes back up again, 75, it comes down, and then that continues on until it stops. You know how many times it's going to bounce until it stops? I sure don't, but this is kind of a wonky one. I can take the sums of my downs plus the sums of my ups if I want, or check it out. All except for the first one, all those are going to be the same, right? It's going to be the same distance times 2, won't it? So if I summed my first up, okay, and I summed up all my ups times 2, I'm going to get all those. So I'm thinking 30 plus my infinite sum from n equals 1 to infinity, because I don't know when it's stopping, but how far did it go up right there? Well, that's my 30 times my 0.75, right? So that first travel up right there, what was it? 22.5 feet. So if I take this, 22.5 is my initial up value, times my common ratio of 0.75 raised to the n minus 1. Ooh, I can find my height on any bounce I want, right? Because this is going to give me my height at any bounce. Now notice, however much it went up, hey, it went down the same amount. So what can I do? I can take that sum times 2. And that's going to sum up all of these guys until it stops, plus my initial 30 that I got there. So I'm going to hit pause. Why don't you go through and see if you can solve it out here quick. Okay, so the first thing I did is I took my 30 and I'm bringing my 2 times my sum. Well, because this is an infinite sum with r less between 0 and 1, or the absolute value of it being less than 1, I'm going to take this and plug it in there and say 0.75 to the power of 0 is 0. 0.75 to the 0 is 1 times 22.5. That's my first term. And then that's over 1 minus my common ratio. There's my r, which turns into 22.5 divided by 0.25. times 2 plus 30. Well, 22.5, oh, that's quarters. I love dividing quarters. Well, that's like thinking $22.50 has 90 quarters in it. If I take my 90 times 2, that's 180 plus my original 30-foot drop. That ball is going to travel 210 feet by the time it finally comes to a rest. Okay? That's a lot. But what do you guys have to do for the rest of the day? Your 8.5 try on your own, day 1. Okay? And also, don't forget to check It's Learning for that potential formative that might be posted in there. Hey guys, hope you have a great weekend. Thanks for playing math with me today. Kruger out.